Look up at a star, and you are seeing a massive sphere of burning hydrogen and helium. Look down at your own hands, and you'll find a rigid framework of calcium and phosphorus, two vastly different states of matter. Yet, if you look past the heat and the texture, you find a shared origin. Everything in the known universe, from the core of a star to the marrow in your bones, is built from a single menu of just 118 ingredients. We often treat that menu as a static poster on a classroom wall, a grid of symbols meant for rote memorization. It's presented as a vocabulary list for a language we never actually learn to speak. But this grid is an infallible predictive map. It is a coordinate system that dictates exactly how the physical world behaves and interacts before the chemicals even touch. What physical, architectural difference separates a heavy bar of gold from the invisible oxygen we breathe? To find the answer, we have to look past the electron clouds and zoom into the dense nucleus at the center of the atom. Here we find protons. The count of these particles is the atomic number, the specific, unchanging metric that defines an element's identity. Consider carbon, the baseline for all known life. Its identity is defined by a nucleus containing exactly 6 protons. This identity is fragile. If we force just one additional proton into that cluster, the internal math of the atom reorganizes. Adding that 7th particle turns the solid carbon into nitrogen gas. It doesn't just add weight, it transforms the substance's entire physical nature. Identity is mathematical. By changing the proton count by 1, you can flip a substance from a toxic hazard into a harmless, non-reactive gas. While the nucleus determines what an atom is, its external boundaries determine how it behaves with its neighbors. Orbiting the core are the valence electrons. These particles, locked in the outermost shell, act as the gatekeepers for every chemical interaction in nature. The vertical columns on the periodic table are a direct map of these particles. By looking at an element's position on this grid, we can tell exactly how many outer electrons it possesses. That count is the sole predictor of a substance's reactivity. It is the reason why one metal will explode the moment it touches water, while another solid metal remains perfectly inert for centuries. An element's personality is the predictable result of its place on the grid. Elements rarely stay isolated in the void. There is a mechanical imperative that forces them to interact. In chemistry, this is the Octet Rule. It is a drive for stability that pushes atoms to acquire exactly 8 valence electrons in their outer shell. Look at an atom with 7 outer electrons. It is close to equilibrium, but that single empty slot creates a physical imbalance. Lacking that final electron creates a state of high tension. The atom is unstable, vibrating with a mechanical need to fill that gap. This search for a perfect 8 count is what drives atoms to bond. It is the mechanical force that turns a collection of individual elements into the reactive world we see around us. To satisfy the Octet Rule, atoms will take what they need from their neighbors. This creates an ionic bond, the permanent theft of an electron. When one atom loses a particle and another gains it, they become oppositely charged, locking together. When a sodium atom, which has 1 extra electron, meets a chlorine atom, which is missing 1, the exchange is violent. The sodium ejects its particle, and the two snap together into a rigid magnetic tether. This theft resolves their instability. It takes a reactive metal and a toxic gas and locks them into the repeating, stable crystal structure of table salt. But atoms don't always steal. Some fulfill their numerical needs through a cooperative partnership. In a covalent bond, atoms merge their outer shells to share electrons. This shared custody allows oxygen and hydrogen to achieve their perfect 8 count, forming the liquid water that covers our planet. As we zoom out from individual interactions, we see how they scale. These microscopic bonds repeat and multiply, building the complex webs that sustain life. The oceans, the atmosphere, and the DNA in your cells are the results of this dance. The vast, infinite complexity of the universe is simply the outcome of 118 basic ingredients ruthlessly balancing their microscopic math.